My name is Yusei Nishiyama. I'm going to give a talk entitled Building iOS at Scale. I tried to make my presentation as practical as possible, so things I'm going to talk about is something you can try out just after you go back to work. Before I get into my talk, I'm going to give you a little bit background of me and my company so that you can better understand the context of the talk. Now I live in England, but I'm originally from Japan and work for a company named Cookpot, which is a company which is the largest recipe sharing service in the world with the aim of making everyday cooking fun. We cover 67 countries and 21 languages and have around 100 million of users all over the world. We have headquarters in UK and Japan and branch offices in Spain, Lebanon, Indonesia and some other countries. We have 10 iOS developers, 4 of them in UK, 4 in Japan, and 1 in Lebanon and 1 in Colombia. Working for the app, which supports a lot of users all over the world in a distributed team, involves tons of challenges. This is going to be a long talk with 100 slides which covers different topics. So I'm going to show a basic structure of the talk so that you can understand how each topic relates to each other. The talk can be divided into 2 main parts. One is working in a large team, and second one is working with large code base. And each part has different topics. The first part covers Fastlane, Danger, and code metrics, and the second part covers build time reduction and code modularization. Let's move on to the first topic, working in a large team. If you work in a team, you may have issues that you never have when you work alone. For example, someone blocks the build and the rest of the team don't know how to fix it properly, or someone's vacation may prevent the team from making a new release because there's only one person who have a distribution certificate. And code review also can be a problem in a big team because imagine you submit a pull request which contains a lot of small mistakes and more than 10 developers start reviewing your code at the same time. You're going to give a massive feedback and it takes ages to deal with all of them. Generally, you can deal with those common issues with continuous integration and automation. None of those tasks should be developer dependent, and you should spend any time for what machine can do. So I'm going to show how we automate those processes in Cookpot. When you say CI, it should consist of several subsystems. This is an overview of our CI system. The diagram starts from the point where developer pushes his or her change to GitHub. GitHub triggers a Jenkins job through webhook. Then Jenkins executes Fastlane scripts. Fastlane is a suite of tools that makes it much simpler to automate mobile developers' daily chores. You can define your custom workflow in a text file called Fastfile. We have 7 fast files which have 28 lanes, and the total line number of the script is more than 700, so which is obviously bigger than the typical starter example. Fastlane is now very popular among mobile developers, and you might have been familiar with some common use cases like running tests or uploading your app to Hockey app. So I'm going to show lesser known and a bit more practical examples. Syncing DSIMs. So if you enable bitcode, it's upload server who compiles your bitcode and generate DSIMs. So you will need to download the generated DSIMs from Apple's server and then upload them to crash reporting service, say Crashlytics, so that they can symbolize crashes. This script automates the process. I will not explain those scripts step by step, but I will make the presentation available after the talk, so you can check it later. The next example is simpler than it looks. It logs into iTunes Connect and checks the status of submitting version. And if the status is pending developer release, the script automatically releases the version with posting comment on Slack. Our CI server also automatically builds the app and distributes it to testers for every push to GitHub. But there are some changes you may not want to distribute to testers. For instance, updates of documentation. It just wastes CI resources. So we decided to distribute beta version only when a pull request is labeled as beta distribution. Getting labels from GitHub is also very easy with Fastlane. Fastlane has GitHub API action with which you can call a GitHub API through Fastlane. Those lanes in the example fetch labels from of a specific pull request and check if it contains a beta distribution label. As I mentioned, in Cookpot, each push triggers a beta distribution to internal testers because dogfooding is a great culture. Members in a company should be one of our best users, and if their feedback is really valuable, we can find a lot of problems and things we can improve from those internal testers before shipping a new feature or new versions. But unfortunately, it can happen automatically. There's a lot of developing features in different branches, so if we developers then doesn't communicate with testers well, they stop giving us feedback because they can't know what we want them to test. So we are going to lose a great opportunity of feedback. One thing you could do is tell them the purpose of the build through the icon. So this Fastlane script appends a badge on the icon. You're going to get badges like that, and it makes communication with developer and tester much easier. For example, we can say, so we are going to release a new version, so please check the latest release candidate. And testers can easily identify which one is from release candidate branch. The next part is about Danger. Before talking about Danger, let me ask a question. Have you ever posted a comment like that? So like, please remove parentheses surrounding the condition. This shouldn't be done by you, but by machine automatically. This is where Danger takes its place. Danger runs on your CI process and automates common code review tasks with the philosophy of leaving developers to think about harder problems. All you need to do is to define rules that every pull request should meet in a text file called Dangerfile. I will not dig down into the detail of Dangerfile, but one important thing is you can execute linter through Dangerfile. So Danger comments on your pull request on behalf of you and warns the author of violation of the rules. So you no longer need to spend your time to pick minor styling mistakes, like say, please remove to do before merging the branch, or that the parameters should be aligned vertically, or the line exceeds a character limit. So you shouldn't spend any time to comment like that. The next part is about code metrics, where our system becomes a bit unique. We collect our code metrics in a database which is called InfluxDB. InfluxDB is a data storage which specializes in time series data. As it has built-in HTTP API and there's a lot of client libraries in many languages, it's very easy to integrate InfluxDB into your build system. And one more important thing I want to mention is it's written in Go, so it's really fast and really responsive. For example, we have Fastlane script which collects code coverage and posts the data to InfluxDB. Those data collected in InfluxDB is read and visualized through Grafana. Grafana is a metrics dashboard and editor and supports InfluxDB as a data storage. So this is an actual change of our test coverage visualized in Grafana. Our code coverage, to be honest, is not great, just above 20%, but we at least say it's getting better. So if your metrics is visualized and accessible, everyone can be aware of something good and bad happening in a team. So that's really important. So that's why visualization is really important. We also utilize InfluxDB and Grafana to measure other metrics like number of issues and number of pull requests. So we can use those data to see how our team is productive and how stable our app is. For example, I think it's very common problem that the developer doesn't spend enough time to code review, and someone claims that we should spend more time for code review. But how can we know how bad we are, and when we can say we are good enough? So to make it clear, we started measuring how long each pull request takes to get merged. So now we have clear evidence it's getting worse, so that we can set a clear goal, like we can say we have number X and we should target number Y. Okay, let's move on to the second part, working with a large code base. Let me explain the problem I want to discuss here through a very simple example. I think it's a common situation where you need to improve registration screen to reduce an abandonment rate. So let's go through what you need to do step by step. Firstly, you need to implement the design. When you finish it, so you hit the run button to check whether it's working as you intend. You find a bug in layout. It's caused by, say, misconfigured content hanging priority, so you fix it, then run again. Unfortunately, you find another bug which only occurs on a specific version of iOS. So you fix it, then push the change to GitHub. Your CI server starts building your branch and runs tests against it. CI fails because you broke a test. You fixed it and run the test locally, then push it. You need to wait for CI again. So the question is, how many times did you build so far? And more generally, how long do you usually wait for build every day? If it's just a simple personal project, it should be okay. But once the size of your code and the size of the team become big enough, it's going to be a serious issue. So there are several techniques to measure and improve Swift build time. In this part, I'll show you how to improve Swift build time and gain productivity in two parts: measurement and improvement. Please don't worry, I will not talk about those nonsenses. So do you remember so when Swift came out, someone says, so you should annotate all types explicitly, or you should should put every code in a single source file, but it's a kind of nonsense. Alright, first thing first, measurement. Needless to say, if you want to improve something, you should start from understanding the problem. The first thing you could do is enable show build operation duration flag. It displays build time on Xcode so that you can always be aware of your build time. But it's not enough, since build process can be broken down into multiple processes, such as dependency management and compilation of each source file, and you may run linter and formatter in run script phase. You need to know how long each process takes to identify the exact bottleneck. Fastlane does a great job here as well. Fastlane generates a report as a XML file with which you can get a good insight of how long each process takes. As it's just a JUnit style XML file, Jenkins can render it as test results. So this is this example is specifically to Jenkins, but you can pass the path to the XML file in a Jenkins console. In the Jenkins console, you can check which length were executed, how long they took, and whether they were successful or not. And ordering by duration, you can see where the bottlenecks are. It says it took 5 minutes to archive and 2 minutes to test. So if I need to improve total build time, I would start from those two parts. So now we know how long each process takes, but you still can break down the compile phase into compilation of each function. An easy way to find a function which takes long to compile is to enable one long function bodies flag. If you turn the flag on, Xcode warns you of heavy function. In this example, I set threshold 100 milliseconds, and Xcode complains because the function took 15 seconds to compile. You also be able to let the compiler print out how long each function takes to compile with debug time function bodies flag. So you can play with those data just by copy and paste it in your terminal, but copy and paste is not tooling friendly. So, but don't worry, those build logs are available under derived data. The extension of the log file is xc activity log, but it actually is just a gzip file. So you can unzip it and read it as a plain text. Let me show an example of how to utilize the data. With the build log, one of my colleagues developed a Danger plugin which comments directly on a function that takes too long to compile. So it gives us more chance to consider if there's any other way to write this function in a compiler-friendly way. Alright, the next part is about how to improve it. In this section, I'll show you how much my idea worked with real data from real application. This application consists of 40,000 lines of Swift code, and so it's not very big, but it's not very small, and uses CocoaPod as dependency management tool. it has 38 direct dependencies to pod library and ends up installing 60 libraries. So the green dot indicates it took 48 minutes to test and archive on CI. So that's really bad. So we should do something for it. The easiest but the most effective technique is to use whole module optimization. So with whole module optimization, Swift compiler compiles all files in a module at once. The intended benefit of whole module optimization is to let the compiler optimize code more aggressively, but there's a bit hacky technique with which you can tell a compiler to compile the whole module at once, but without any optimization. So you can try this out by setting optimization level whole module optimization and specifying optimization level none in other Swift flag. I think in a previous year there's a talk about build time reduction, and the talk really explained very well why it works and what's the pitfall of this technique. So you also can check it out to know much about this. Whole module optimization without any optimization, to be honest, may sound really weird, but it makes the build time really fast in most of the cases. So with the setting, now CI takes less than 20 minutes to test and archive. Before I try more ideas, I'd like to get more detailed build time information by enabling debug time function bodies flag, which I explained in a previous slide. Compilation times is also logged in our database, so we can investigate the data through our console. I found some libraries called this slow build. So you can see that the first two time-consuming functions are from RX Swift. So I decided to manage some huge Swift libraries with Carthage instead of CocoaPods. So with Carthage, Xcode doesn't need to compile those frameworks every time you run the application because Carthage pre-builds those libraries. Now Carthage saves 10 more minutes, so it finally improves the build time by 85%. By the way, Xcode 9 introduces new build system. It's written in Swift, and it's promised to be more performant than the old one. I compiled the project with Swift 3.2 and new build system, but unfortunately, at least for our case, I can't see any significant improvement in build time. Maybe because the new build system is still a preview version, but it's still worth trying because it gives more better feedback than the old one. Okay, so though I've already saw great improvements in build time already, but it still takes a considerable amount of time. So here one question came to my mind, which is, do I really need to build the entire application every time? So the answer should be no, because now we have Playground. So Playground is more than a repo environment, since it can render builds. So we can use Playground as a powerful prototyping tool, and the workflow should be like that. So you can test your idea in Playground. It can be anything. You can test interface and design. Even you can use it to reproduce a bug with a minimum amount of code. Then once you confirmed your idea works, then you move those code into your application project. So Playground seems to be the answer to my question, but it's not 100% true, because generally speaking, it's very rare that your code doesn't rely on any existing code. So in a real-world prototyping, so you may want to use existing code for prototyping. So ideally, you should have separate modules for each purpose so that you can play with them in playground easily. So in this example, I have my own UI framework, which is imported from both playground and application project, and we can access custom color schemes through playground. So what will happen if you evolve the idea of having separated modules for each purpose? It's going to be called modularization. In 2014, James Lewis proposed a microservice architecture. In short, the microservice architecture is an approach to develop single application as a suite of small services. It doesn't fully correspond to what I'm going to talk about because this is about web application, but we can get very similar benefits from the idea. So if you apply the idea to apps, you will get this kind of architecture. So you have core frameworks such as design framework and networking framework and persistence layer, and you can build each feature on top of those core libraries. The benefit of code modularization is more than just keeping your project cleaner. As the default access level of Swift is internal, everything you put into your framework is private from other frameworks as default. So it gives you more chance to consider which method and properties should be public or private. Another benefit is that you can get faster incremental build time. A change you make to a module doesn't trigger rebuild of other modules. So it would improve your incremental build time dramatically. Another thing you could get from code modularization is autonomous teams. Let me explain. As we grow up, it's hard to synchronize teams each other. And it takes months to get a stable version because it's really hard to make sure that a change to a feature doesn't break any other features. So if there are clear boundaries between modules, people can focus only on the module they are working on without taking care of what others are doing. So it enables you to build autonomous team and make release easier. So to make your app modular, the first thing you need to consider is repository strategy. You of course can put all your developing frameworks into a single repository. And the main benefit of the approach is that you don't need to change your workflow. You can work with your frameworks as you did for single monolithic application. The downside may be those frameworks are not ready to be open sourced. And you can manage your frameworks in different repositories. One obvious downside of the approach is that it makes your workflow more complex. Imagine you are developing a new feature which requires changes to your main application and changes to your framework, say networking layer. So you may need to submit two different pull requests. One is to your main application, one is to API framework. So it obviously makes your workflow more complex. The next step is to consider how to manage dependencies. I will compare those for possible approaches. CocoaPod's Git submodule, and Carthage, and Git subtree. CocoaPod has been a de facto standard among iOS developers and still one of the best dependency management tools. So all thing you need to do is to define dependencies in pod file, and CocoaPod manages everything else. And to put it the other way, so there's a lot of things happening under the hood, and it makes things harder when you face a problem. The next one is Git submodule. Strictly, it's not a dependency management tool. It just checks out dependent repositories for you, and everything else is up to you. You can gain full control over it. While you have to introduce an extra complexity in your workflow, because every time you make a change to your framework, you need to update the reference in the parent repository to point the new commit. Carthage is kind of middle ground approach between CocoaPods and Git submodule. You define dependencies in cart file, and Carthage downloads them for you. But how to link them is up to you. Carthage also previews library, so Xcode doesn't need to compile and index them. So it saves a lot of time. One thing you need to take care is AVI stability. As Swift's AVI stability is not stable yet, all your previewed frameworks must be built with the same version of Swift compiler. By the way, discussion of Swift 5 has been started already, and AVI stability is their primary focus. So this is not going to be a problem anymore. The last one, which probably is a bit less popular than others, is Git subtree. It clones the sub-project and merges them into the parent project. So you can make changes both to the parent project and the sub-project in the same place. Then, when you push those changes, Git subtree goes through the commit and pick the changes that should go to sub-projects. So with the magic of Git subtree, you can work as if you worked in a single repository, but it actually is backed by multiple repositories. The pros and the cons are mostly same with Git submodule, but one significant advantage over Git submodule is that you don't need to change your workflow. A downside is you need to run the bit tricky merging strategies of Git subtree. Otherwise, you will have a serious conflict or dirty Git history. So the link is a link to the Medium post where Medium engineer in Medium explains how they modularize their code with Git subtree. So I highly recommend to see it. Okay, so the lesson learned. So if your app is a huge monolithic application, to be honest, code modularization is not a very simple task and requires a lot of careful planning ahead. Once you decided to do that, then you should start from single repository, because at the beginning of the process, your frameworks must not be very stable. And moving back and forth between repositories while making changes to them slows you down. Then after a while, you will get a point where your framework is not changed very often. Then you can consider separating them into multiple repositories and use previewed version of them. But there's a common pitfall of code modularization, which is dynamic framework loading time. So you can check how long dynamic library loading takes by enabling dy ld print statistics flag. If an app takes very long to open, the system kills your app. So I had some people work around this problem by merging all frameworks into a single dynamic framework and link it to an application. But it's not very simple solution. So dynamic library loading time was the only concern for moving this idea forward, and it seems not to be very encouraged by Apple itself. So I was still in two minds whether I should encourage this approach to everybody or not. But the concern has been gone because now Xcode 9 starts supporting Swift static library. So now I'm pretty sure this is a way to go. Let me recap. Automate your daily workflows with Fastlane and CI. And Danger saves you time for code review. And visualize everything you want to improve. And revising project settings may improve build time. And code modularization improves build index time and also helps you getting a well-structured team and code base. So I hurried to finish my my talk, but don't worry, this talk is already available on the link, so you can check it out now. And yeah, that's pretty much it. Thank you.
Hi, thanks for the talk. I'm really curious about how you solve working with playgrounds. I mean, if you build new components, that's probably easy to build them in Playground and then move them to app. But do you sometimes take the existing code and move it to Playground to fix it, or if it's already in the app, then you work there?
So your question is how to move the code to Playground?
Yeah, because sometimes there could be just too many dependencies on the code to easily move it. So do you have a solution for that?
So to be honest, I don't have any solution. You need to modularize your application from bottom to up. So I think that's the only way. So you need to build a building block from bottom. I mean, like API layer or utilities. Yeah. And building them from bottom. I think that's the only way.
Thanks. Okay.
Could you please provide some examples of the particular modules in your particular app? I mean, how do you divide your app into modules, and some common practices maybe? What should you extract in a separate module and what should not?
So I don't have actual code in my machine, but we have networking library and API framework and UI framework and data and persistent library and utilities. And it's still now in a we are still in a process, but we are planning to have a framework for each feature on top of those frameworks. Am I answering your question?
At the very end, you've been showing the problems with dynamic libraries loading and the new solution of using the statically linked libraries. Do you know if there is already support for the building statically linked libraries and linking them into CocoaPods on Carthage or any other like the usual solution, or is it something that is in the works still?
So your question is how to deal with dynamic loading time with Carthage? Sorry.
The question is whether there is already a support for linking frameworks statically inside the Carthage and CocoaPods. So is it something that I can use like today?
Okay, I I saw a pull request which is to Carthage, which is for supporting static libraries. So I think they've already supported them. Do I answer your question?
Cool. Thank you. Thank you very much.
So, thank you.